All right, so the next thing we're going to look at in here is going to be kind of the changes. We talked a little bit about changes to the heart, acute changes that happen in the heart in response to exercise. So what we're going to start looking at now is a little bit more of what's happening actually in the blood or in distribution of blood. So one of the things we will see in response to exercise, cardiovascular-wise, is an increase in blood flow. And specifically more so blood flow to those working muscles, and they're going to be getting a bigger portion of that cardiac output. So we would call this rise or increase in blood flow to those areas exercise hyperemia, just kind of saying exercise causing increased blood flow to that area, so hyper, more, emia, blood. Like I said, during exercise, we're going to see a lot more blood flow going to these working muscles, and again, getting a bigger portion of that cardiac output, which is not going to be true of non-working muscles. So during these increases in activity, you're going to see over 3/4 of the cardiac output going to these working muscles. We're also going to see opening of the blood vessels to those muscles. So we're going to see this vasodilation to allow more blood flow to get to those areas. And again, areas that are not involved in this activity are going to be seeing decreases in blood flow. So things to like the kidneys, the digestive system, we're going to see a lot of vasoconstriction in those areas, limiting blood flow to those areas, making sure it's going to the muscles. Because again, as we've been talking about with bioenergetics and everything else in this one, to generate ATP, we need oxygen getting to the muscles. How we deliver that oxygen is by blood flow, and the more blood that we can deliver to the muscles, in theory, the more oxygen we can deliver, and then also in theory, the more ATP we can generate, therefore the muscle can work harder. Again, anything that is having the blood go different places, so to the skin, to the digestive tract, anything else there, that's blood that's not going to the muscle and therefore is going to reduce that output somewhat. So this is from one of the textbooks I didn't have you get. This is from the Advanced Cardiovascular Exercise Physiology, the book sitting below me. This is kind of showing you that hyperemia that happens there. So we're really talking about vasodilation happening. And really what triggers a lot of this is actually going to be these local changes in the muscle. So we're going to get a decreasing pH, a decreasing O2, increases in acetylcholine. All these factors act as local vasodilators. This vasodilation can open up there, and a lot of times what we get happening from that local vasodilation is what we call conductive vasodilation, which is then once we have this local area opening up the blood vessel a bit more, it's going to start working its way back to those main blood vessels to open up that pathway. This myogenic autoregulation is just the idea that that we can get vasodilation, vasoconstriction. So the brain is also going to be, the vasomotor center is going to be doing some myogenic autoregulation, that opening up these blood vessels to that area. One of the other things that helps with this hyperemia is the fact that as we contract these muscles, it is going to help with venous return and therefore blood output. And the really interesting one here is the force of the blood and increased blood flow against the blood vessels leads to a shear stress. So it kind of stresses those cells that are lining that blood vessel. That stress leads to increased nitric oxide production and release, which nitric oxide is a vasodilator, which is going to lead to that increased vasodilation. In the simple sense here, what we're doing with the blood flow is opening up blood flow to those active muscles to deliver more blood and therefore more oxygen to those tissues. The other place we're going to see increased blood flow here is going to be to the lungs. We're going to get increased blood flow as we're getting more blood returning to the right side of the heart, and the activity of the heart is going to increase. Again, in order for this to happen, we do need that increased venous return, and that's true of also the vasodilation. If we are not getting this adequate venous return, we are going to get a drop in blood pressure and not good delivery to this one. So any of these increases in blood flow to a particular area through vasodilation need an accompanying increase in that venous return to the heart. And what you can see on these ones is you start looking at where the blood starts going at rest versus during exercise. You can see at rest is in the red here. At rest, you can see the red is the bigger portion of a lot of these ones. The red is the urinary tract and the digestive tract. And you can see as we get even into light exercise, that reduces by half, and we see almost a doubling of blood flow to the muscles. And I kind of put a big thing right here to kind of point it out here, but you see as exercise gets from light to moderate to maximal, you can see the portion of cardiac output going to the skeletal muscle becomes bigger and bigger and bigger, and again, getting to be 85-90% almost of that cardiac output. The other thing we can see is not only is it a bigger percentage of that cardiac output, as we go from rest to light to moderate to maximal, the other thing we're seeing is we also see like a 5-fold increase in cardiac output. So, I mean, if we're talking overall volume, it's taking up a bigger percentage of that, but we're also talking a much larger volume, a lot more liters per minute being sent from the heart than there was at rest. So overall, much bigger delivery of blood and therefore oxygen to these working muscles under exercise. So again, looking at some of these other ones here, some of these were in the first show, some of these were in the second one here, but some key points, at least in terms to cardiovascular response. As exercise intensity gets higher, we're going to see increases in heart rate, increases in stroke volume, and because both of those increase, we will see increases in cardiac output. This means we're pushing more blood out, and that is to deliver more oxygen and nutrients to those muscles so we can continue to work them, as well as get rid of any waste products they are generating so they can keep working without having a buildup of waste. We're going to see definitely changes in flow distribution, directing blood to those muscles and away from systems that maybe aren't being as active at that time, or because the muscles are calling so much for it, we will reduce flow to things like the digestive tract and things like the urinary tract. Cardiovascular drift happens over a long period of time, especially also in the heat during a steady state exercise. What we see over time, we get decreased stroke volume, so you'll see this gradual climbing in heart rate to make up for that and maintain that steady state exercise. We know from what we talked about before, blood pressure is pretty, at least the systolic, pretty linear to changes in exercise intensity, while the diastolic pressure remains pretty constant or maybe even drops a little bit. And anything that is a high resistance thing here, anything where you end up holding your breath, you will see very large spikes in blood pressure. So another thing to look at with the blood that we see changing during exercise is what we call the arterial venous oxygen difference. So this is basically, we've talked about all the ways that we're getting more blood out of the heart, more blood to the tissues through that vasodilation. A big thing though is if the cells are going to use that oxygen, it has to leave the bloodstream. And one of the ways we can kind of see this is look at arterial blood versus venous blood and see how much oxygen is still present. So if there's less oxygen in that venous blood, so let's say we go from 99% saturated hemoglobin to 50%, we know we dropped off 50% of the oxygen we were carrying. If we start seeing under exercise bigger differences between that arterial and venous blood, we are going to realize that more is getting dropped off at the tissues and therefore more is getting used. So what we're looking at is the oxygen content in arterial blood versus venous blood. As exercise increases, we should see a corresponding increase in the amount of oxygen being taken out of the blood. And when we look at VO2, and we've talked a bit about VO2 and VO2 max, but VO2 is that cardiac output times how much blood we're dropping off at, not blood, but how much oxygen we're dropping off at the tissues. So again, those are two different ways we can, and as we start getting into things that exercise might change, you can kind of see here. We talked about VO2 max being the standard here. Cardiac output is a piece of that. So if we have changes to the cardiovascular system that increase that cardiac output, those could definitely change your VO2 max or your VO2. The other thing is if we can get more efficient at dropping off more oxygen, those are other ways that we can actually get these increases in VO2 max or in our VO2 if we're looking at a submaximal level. And again, it's that whole Fick equation, not so worried that you remember the name of it, but understanding that kind of how much consumption of oxygen your tissue is doing are a combination of your cardiac output and how much oxygen is getting basically delivered to the tissues. And one of the things you can kind of see here is this is looking at this bottom one here with the squares is looking at venous content of the blood and how much oxygen is there. You can see is intensity. These are intensity levels. As intensity increases, you can see the oxygen level at rest. We're dropping off some oxygen, but not a ton. As we get in higher and higher intensities, we can see that between that arterial blood, which is staying pretty constant, actually going up a little bit in terms of oxygen levels, you can see the venous content is dropping as the intensity increases. What this is meaning is that there's less oxygen left in the venous blood, which the opposite of that, the corresponding thing that goes with that is that means that more oxygen is getting delivered to the tissues. We're going to see that there's a number of factors that influence this. So if we start looking at the tissues can release a number of different factors that can help change this. And what we can talk about here, and we talked about this a lot in A&P, but you had that hemoglobin saturation curve, that affinity of the hemoglobin for oxygen. And what we can see, and what we refer to as the Bohr effect, is the fact that the local environment can affect how well oxygen is holding on to, how hemoglobin is holding on to the oxygen. So again, what the Bohr effect is really saying is the amount of oxygen released at the muscle is going to depend on what's going on at that muscle. So we're going to see there is a number of factors that can influence this. So partial pressure of oxygen there, the pH, the partial pressure of carbon dioxide, temperature, a substance called 2,3-diphosphoglycerate, or DPG. This is produced in red blood cells, like it says there, during prolonged heavy exercise. What 2,3-DPG does is it actually reduces the affinity of the affinity of hemoglobin for oxygen. What that is going to mean is if these cells under exercise are producing more 2,3-DPG, it's going to mean that it's going to unload or be more willing to dump off that oxygen at the tissues. And again, the Bohr effect here on this one, it is doing a right shift of the hemoglobin curve. So if you remember the hemoglobin curve, that kind of S-shaped curve here, this hemoglobin saturation, as you get more and more partial pressure of oxygen in the air, more and more hemoglobin is going to be bound. We know at sea level that the saturation should be about 99 to 100%, 98, at worst 97 type of thing like that. What we know from A&P2 is that there was a number of different things. Increased levels of oxygen make it so it holds on a little bit better here. If we get more and more carbon dioxide binding to hemoglobin, it actually right shifts that or makes it less efficient at holding on to that oxygen. Increasing acidity levels right shift these curves, make them less efficient at holding oxygen. So if you compare these two curves right here, let's say at this area right here, this one, not a high partial pressure, and percent saturated is quite high. You can see right shift, and it takes a much higher partial pressure to saturate it to a similar level. What that is saying is the hemoglobin is not holding on to the oxygen as well. But again, you can see here, high acidity, right shifts this curve, makes it less efficient. And temperature, which the temperature at the muscles is going to be up, makes it less efficient at holding on to that oxygen. All these things that make the hemoglobin less efficient at the tissues holding on to oxygen mean we're delivering more oxygen to those tissues. In other words, getting a bigger arterial venous change in those oxygen levels. So like it says here, a change in the environment leads to pH and oxygen levels decreasing, temperature and carbon dioxide levels increasing. What effect will these changes have on the amount of O2 released to the muscle? Well, we know increased carbon dioxide, increased temperature both make hemoglobin less efficient. So this should, increase oxygen release. So now on this one here, a change in the local metabolic environment has, again, pH, oxygen levels have decreased, temperature and CO2 levels have increased. What do these changes in the local environment suggest has occurred? It's basically saying that the muscle is consuming oxygen and generating carbon dioxide, and along the way, because it is working, creating an increased temperature. So all these things would say that the muscles probably started exercising from a resting state. The other thing we see during exercise is we will actually see a little bit of a drop in the blood plasma volume. This is going to be especially occur more often in hotter temperatures. Anytime we're losing water to do cooling, so anything with sweating, and we'll get into this a lot more as we talk about effects of heat in other chapters after we get through some of this stuff here in the first few weeks. But increases in sweating, that is going to cause us to lose plasma volume. And this is going to cause that plasma volume to drop, especially if we're doing something in really hot weather. And again, if we're looking at effects of hot weather, just to kind of give you an idea right now, is in order to cool the body, we have to send blood to the skin to actually cool that blood. That the sweat, when it's evaporating, it'll cool that blood, cools over all the core. Part of the reason that people cannot perform at as high a level in especially really hot and humid environments is very simply we're sending more blood to the tissues. If we're sending blood to the tissues, where are we not sending it? We're not sending it to the muscles. And if the muscles don't get that blood, less oxygen is getting delivered to the muscles. Level of output that those muscles can do is going to be decreased, especially as less and less blood can go to those muscles. Again, starts to be a little bit reduced even if you're not sweating, in that you're going to, because of increases in blood pressure, you are going to push more fluids into the interstitial space. If you're sweating a lot, we're going to see even larger drops in that plasma volume. Again, like I was already saying, with temperature, it starts to be an issue again in terms of sending some of that blood volume to the skin. But if you lose enough blood volume due to the fact that you're sweating so much, it is definitely going to impair your performance and cause you to have to slow down. You're going to have issues with maintaining blood pressure. It does lead to an increased hemoconcentration of blood cells. So your hematocrit would actually look higher during this. But again, blood volume is decreasing. So again, some other key points to go through again here. That arteriovenous difference, it increases as venous oxygen concentration decreases during exercise due to the body or the muscles taking more oxygen from that blood. Plasma volume is going to decrease as you push more into the interstitial spaces, as well as lose volume as sweat. And this is going to lead to hemoconcentration of the blood, higher concentration of red blood cells, increasing carrying capacity per unit of blood, but again, you have less units of blood. And again, blood pH, as we start doing more of this work, is going to increase acidity in here, which if we actually start looking at arteriovenous effects, this will also decrease our ability of hemoglobin to hold on to that oxygen. And again, as I've said this a couple times already, but that change in arteriovenous blood is really pretty much a direct reflection of that oxygen getting taken up by the active cells. If we're using those in those muscle cells, that means there's less to be available to come back in the venous blood. And again, the more we can drop off, and again, this is what we can see when we start getting to long-term adaptations and increasing our endurance and increasing our performance. You can actually start seeing changes earlier on in those cardiac output things, cardiac output measures. So increases in stroke volume, increases in efficiency of the heart. Longer term changes, we start seeing more and changes in that ability to extract more of that oxygen. But again, it's the combination of these two things that is going to lead to changes in that VO2 max over time. So we'll look at some other factors here that change acute-wise during this. It'll be more of some of these respiratory and muscle changes, and I believe this is about it for our cardiovascular ones. So I'll see you next time.